Look at the sheer scale of this track. We're flying through a 5,000-piece LEGO Rube Goldberg machine, a sprawling, colorful fortress built with a singular purpose, guarding that oversized sunflower seed resting right in the center. Getting to that pedestal presents a massive engineering problem. A system like this relies entirely on gravity and exact mathematical precision. Every ramp, weight, and pendulum has to trigger at the precise right millisecond for the chain reaction to hold together. But mathematics implies predictability, and engineers know that the greatest threat to any controlled system is biological variance. Introduce a live hamster into the middle of this rigid architecture, and you introduce a highly mobile, chaotic variable that operates on instinct instead of equations. One wrong step, one unexpected pause from our runner, and the entire physical sequence stalls out. Navigating this course becomes the ultimate stress test of strict physical laws pitted against unpredictable biology. Inside this setup, the hamster operates as the system's living battery. All of these gears and tracks are completely inert without the animal's kinetic energy to kickstart the process. The first point of contact relies on a highly specific interaction. Our athlete has to step up and physically engage with a specialized gold-plated LEGO lever to begin the run. Right here, as that tiny golden lever is pulled down, you can see it instantly releases a bright red glass marble down the smooth track. That single marble drop triggers an immediate high-speed domino sequence. Blocks topple, ramps drop, and the entire machine locks into an aggressive forward momentum. The physical threshold is officially crossed. The machine is moving, the animal is moving, and the two are inextricably linked in a shared, unstoppable chain reaction. The first spatial zone forces the hamster into a chaotic, high-speed environment. It has to navigate a highly constrained, narrow path, while a cascading domino track clatters violently right alongside it. Designing this section required solving a difficult mathematical challenge. The heavy, spinning LEGO gears needed to keep the machinery moving, but they had to be shaped and spaced so they wouldn't strike a rapidly moving animal. This schematic blueprint shows exactly how they solved it. By mapping out what engineers call whisker clearance, that highlighted geometric safe zone is measured out to the exact millimeter to match the hamster's lateral physical dimensions. As the gear rotates in the diagram, you can see it creates a brief, cyclic window of safe passage. These incredibly tight geometric tolerances physically force the hamster to alter its natural, sprawling running gait into a strict, linear sprint. The environment demands specific behavior from the runner. Successful biomechanical engineering means the design has to adapt entirely to the physical reality of the user, forcing the biology and the mechanics into alignment. Moving into the second zone, the layout shifts. We get a vertical series of mechanical micro-elevators, rhythmically lifting marbles to an upper deck right above the runner's head. Here, the designers apply a concept called mechanical pacing. Instead of urging the user forward, the system is designed to intentionally stall the runner, forcing them to match the environment's internal timing. And it works. The hamster instinctively pauses its run. It actively sits and waits for a spinning gear to rotate and lock into the correct position before attempting to move forward. That brief, intentional pause marks a shift from a simple biological reaction to active environmental anticipation. The animal understands the rhythm of the machine, blurring the line between its natural instincts and the engineered timing. Then comes the most dangerous vertical segment of the course, a massive, swinging LEGO crane apparatus designed to ferry the sequence across a wide gap. It relies entirely on a gravity drop. The momentum must transfer perfectly from the swinging crane's heavy payload over to the next delicate, stationary stage of the machine. But look at the marble right in the center of the frame. It loses momentum entirely, failing to clear the gap, and rolling to a complete dead stop midway across the jagged, incomplete bridge. The immediate consequence is a total silence. The levers stop turning, the weights freeze in place, and the meticulously engineered chain reaction comes to a dead halt. The perfect machine has failed its half of the bargain. With the track incomplete, the hamster is now completely stranded inside a stalled physics equation. This is where biological improvisation takes over. Instead of waiting for a gear that will never turn, the hamster independently assesses the stalled machinery blocking its path. It actively steps up, physicalizing the solution. Using its front paws, the animal reaches out and manually dislodges the stuck mechanism, bypassing the failure point entirely. That single nudge is enough. The final marble run instantly reactivates, cascading down the ramps as a direct result of the animal's physical intervention. When the rigid, mathematical logic of the engineering broke down, the machine couldn't fix itself. Raw, adaptable, biological problem-solving was the only thing capable of saving the sequence. The final trigger point clicks into place, releasing a massive mechanical shower of confetti and dispensing the giant sunflower seed to the waiting athlete. Looking from this ground floor perspective, straight up at those colorful gears and bridges, you realize the sheer, towering scale of the obstacles this tiny runner had to overcome. It shows us that brilliant engineering doesn't actually exist in a sterile vacuum of flawless mathematics. The ultimate feat of design is creating mechanics that can beautifully harmonize with, and even rely upon, the unpredictable,